a continuation of the previous talk because it's our joint work with Peter, and it aims to illustrate for you our generalization of the same methodologies to more flexible unstructured meshes. So in order to kind of introduce the type of discretization which we use the dual cell approach with the edge-based data structure, which you can see here illustrated in crudely in the two-dimensional for the two-dimensional meshes. So what I will show you usually would be meshes which represent edges, because this is what most of our work from engineering usually shows. And I could see that in atmospheric community, what everybody tends to show are the finite volume meshes, which are the dual meshes to those. So if you see triangular meshes, it does not mean that we integrate on the triangles. We integrate on the, in two-dimensional cases, on the polygonal meshes, which can be represented this way. We also, similarly like with the work you have just seen for structured meshes in OILAC, we also use, we don't use staggered meshes. So all the variables are in the nodal points. I'm sorry, I need to get used to this laptop. So basically what we have done is we have implemented the same numerics as in the codes which you have seen, which in illustration you have seen so far, and we use NFT MP database solvers for this. And in order to see if there is an issue with using unstructured meshes, here we can use hybrid meshes, so we have a full flexibility on what type of mesh we wish to use. So it's only a question of having a mesh generator which you will couple to this type of solvers. So the next thing was to see, can we do the typical canonical problems for non-hydrostatic solvers, which one should need to pass to confirm that the implementation is correct. So the elementary non-hydrostatic model which we have used first is this is an example for non-hydrostatic Boussinesq mountain wave. And the nice thing about this presentation is that we here have a very accurate comparison with in the linear regime with the linear theories from Smith and Duran. And you can see here on your left panel that we can look at the linear regime, and on the right panel you can see nonlinear regime with the wave breaking. So how did we validate this? Is first of all, we have used the meshes in such a way that you can see here the mesh which is being refined behind the hill and in the vicinity of the hill. So the resolution of this mesh is the same as would be for Cartesian mesh, corresponding Cartesian mesh. However, we use twice less points to obtain the solution. So there is a saving in this respect. And the comparison with the equivalent spacing, the structured mesh, and we use the OILAC to make this solution, shows that the solutions are extremely close to each other. And with the comparison with linear theories, you can only see the zoom of the waves. We actually went 7 wavelengths, and on the 7th wavelength we have a 3% difference with the linear theories, and in terms of wavelengths, and 8% in propagation angle, and 7% loss in the wave amplitude. So this is and the same happens when we look at OILAC solution on structured meshes. So bearing in mind that those are theories, it's quite pleasing result for us. The next illustration is, for this we have used an elastic equations, the same type of solution but different equations. So here you have a little illustration how one could use the static adaptivity, and in this case we solve the well-known SHAR problem. On the top panel you may see a typical issue with the SHAR problem. So on the panel A it illustrates that if you are using some form of transformation, coordinate transformation, you may end up with unphysical solution if the mesh is too coarse. On the panel B, it shows that with the same coordinate transformation, if the mesh is refined, your solution is correct. So we started with a very coarse mesh, and the recommended mesh by SHAR was around 10,000 points to avoid the issue. So we started with extremely coarse mesh of 3,600 points, and we started with the Cartesian mesh which aligns with the shape of the three hills at the bottom there. As you can see, well, the solution doesn't look terribly nice, but it's still better. It doesn't have those very unphysical features which you could see on the panel A there. However, it is a bit oscillatory, which is not surprising, bearing in mind that this mesh does not reflect topography very well. So it linearizes topography to the points so we have basically so little points that the topography is not smooth anymore. It's a rough terrain, very rough terrain. So unsurprisingly, this is reflected by solution. However, already this solution provides us with enough information to use static adaptivity. For this, we are using properties of MP data, because MP data, which is advection part of our solver, is constructed from two upwind iterations. The first iteration gives us lower order solution, first order upwind solution. The second one improves on this. So we can use the difference between the two solutions as an error, which we use as an error indicator for mesh adaptivity. And having this information, in this case, in the 2 dimensions, we use advancing front technique, mesh generation. So it's very easy to use the information from the mesh indicator to control the background spacing based on this. And you can see the mesh which we obtained. And here on this panel, you can see that we have got an excellent results consistent with what we should obtain in the literature. Interestingly enough, I didn't refine particularly adaptivity for this problem, so it was just having a first go at it, if you like, without any special work done on this. But still, you can see that we have obtained this nice solution with substantially less mesh points than the originally recommended by SHAR. So it's just one.
Horizontal resolution in that upper constant.
Which one?
The upper one.
Well, it's 3,600. So I think it was 4 times coarser, or if I would need to double check because I did it several years ago. I believe it was 4 times coarser than the SHAR mesh. The one around 4 times coarser. So the resolution here was automatically done. Always when we, well, at least when I do this type of things, there are automatic checks which prevent having too small elements. So obviously we don't allow extremely small spacing to appear, because then we would have time step limitations and so on. So it's a question of experience use of this type of methods to have a realistic mesh adaptivity. And obviously good mesh generators have also control of what is the spacing in the neighboring cells, so you don't have a very abrupt change of the spacing between the neighboring cells. So those kind of things are relatively well known.
Question of clarification. You mentioned that it's advanced front technique.
I'm sorry?
You mentioned mentioned at the bottom mesh is an advancing front technique, right?
Yes.
Advancing front, so it's based on triangles.
Yes, but because, again, I was showing this some time ago to specifically to atmospheric audience, so I made an effort to present this particular mesh in terms of the finite volume meshes. But the edge-based mesh is the triangular mesh here in this case. But we don't need to have this, as you will see in a moment later on. Well, so far we looked at the relatively shallow atmosphere, which was typical to the troposphere. But a very important test case, which kind of is towards what Niels tries to discuss here, is to look at the deep atmosphere. So here, this is a typical for the stratosphere situation, and we have chosen this test case because it was it's very challenging test case, and it was studied by several people, as you can see already. And for this test case, why is it challenging? Is because we have, with the deep atmosphere and much stronger stratification than before, we have because the density is decreasing so much, we have an increase of the basically nonlinear amplification of the amplitude, wave amplitude. So here what you can see is the two equations which we use for this test case. The first one is unelastic equations of Lipson-Hemler, and the second one is pseudo-incompressible equation of Duran, which Piotr already introduced to us as if we are able to have, because in this case we are able to have the same numerics, so partially it kind of relates to your question. How do we compare compressible solutions to unelastic solutions? So here we have a pseudo-incompressible solution, which is more compatible with the Euler compressible solutions. So that's why we are addressing this. So we have those two equations and solved on identical meshes with identical numerics. So it's only the solution, the equation which matters here. And you can see the development of this type of in time. You can see how this flow develops. What is important is that we have here 60 kilometers deep atmosphere, and the hill, very tiny little hill, which is only 600 meters high. So it's a very delicate perturbation for the flow, which in time results in the breaking of the gravity waves far away from the perturbation, around 30 kilometers high. So
Which set of equations are those results for?
sorry?
Which inelastic approach?
Bear with me.
It is for unelastic.
Sorry, those ones are for unelastic. But what I want to point to you now is that we wish to now examine, because that kind of shows the end of the story, when we examine the moment when the wave starts to break. So that's the most sensitive moment at the time of 90 minutes. Then we did a very thorough comparison of this. And what you can see here is the Euler solution at this time. So this is an elastic solution in this case, and on structured meshes with the mapping. And what we see here in this column is the Cartesian mesh, but it's aligned, physically aligned with the shape of the hill. And here we have a full unstructured triangular mesh. You remember that we are solving on the polygons, and again aligned with the hill. What we have in this row is with solutions on those meshes with different equations. So we have here an elastic equation obtained on both meshes, and we have pseudo-incompressible solution obtained on those two meshes. Bearing in mind that there are slight differences for plotting reasons even, you may see that those solutions are very comparable. Moreover, you probably would notice if on closer examination, then the errors introduced, well, differences, I would say, introduced because we use different space discretization by using different meshes is greater than between those two equations. So this is a challenging test case because it is believed that at those conditions, which are for deep atmosphere, the inelastic solvers normally would not be anticipated to work correctly. So you can see that at least for this example, this is not the case. So the differences between the different set of equations was basically on the order of truncations errors. Well, however, we were interested what happens if we increase even more stratification, because there are always people who say, okay, but if you increase stratification, you start to have problems. So we started to look when we will have a difference between the solution, and indeed we found the case. So if we increase the stratification 4 times and we double the wind speed, then we start to see the differences which we actually quantified in our paper in Acta Geophysica in this special issue. So you can see exact error measures there. However, one needs to point out that under those conditions, CV becomes negative. Okay, so we had to stretch the properties of the media so much that it became completely unphysical medium. Okay, so when we were trying to have a realistic atmosphere, we couldn't see a difference. But when we had to push it so far as to go to completely unrealistic. Moreover, we also ran it as a semi-Lagrangian solution with the OILAC to check if it was a question of numerics and so on. So this was all confirmed both with OILAC and on those measures. So this perhaps may add as one of interesting examples to the discussion on those. Okay, let's look at some other progress which we have made on unstructured meshes. So again, this is another canonical problem for verifying correctness of our implementation. And you can see here a low fruit number flow past a 3-dimensional hill. In this case, we have used a tetrahedral mesh. So it's a full unstructured, randomly generated tetrahedral mesh. In this case, we are using the Delaunay triangulation type of the mesh generator, and we have a special treatment with advancing front if we have a very elongated, narrow gaps, which we know that the Delaunay triangulation cannot handle normally. So it is very hard to look at the mesh in this case. Usually you can only observe the surface mesh. So you can see here a cut through. It's in the middle of through the hill, so you have a projection of the edges from the neighborhood. Okay, so that's the only way you can visualize more or less what is the point distribution. In this case, we didn't bother with at present with refining it in any way, so it was more or less similar spacing as the one which we would use for the comparison with structured meshes. So, and the results are in good agreement with the experimental data from Hunt and Schneider from 1980, and with the numerical data by Szmelter and Rotuno as well. Well, because we have with using this data structure, we can do any type of shapes of the cells. So you can see the same solution here on the prismatic mesh. So if you look at the cut in this, looking from above the hill, so this is the computational mesh which we have used in this case, and we have a uniformly spaced prismatic mesh. Again, for this is again kind of a zoom of what you can see. You may hopefully see that there is a regularity in the vertical in the mesh. With most of the visualization program for unstructured meshes require tetrahedral meshes, so you may see they're purposely introduced for visualization additional edges, which actually we don't use in the computation. So what you can see here is, in this case, the comparison between this is the one of the selection of data from at the cut in horizontal, and you can see that comparison on the prismatic meshes and the comparison on the fully tetrahedral meshes is still quite good. Please remember that those meshes are fully non-symmetric. So it is occasionally a big deal in some applications to have a symmetric solution on absolutely random asymmetric mesh. So there is no tweaking, nothing which we do to make the mesh symmetric in any way. Okay, so that shows a quality of this type of approximation, numerical approximation in the solver. Another canonical test case which provides a very rigorous quantitative information is the example of convective planetary boundary layer. So basically it's like water in the kettle. Yes, you hit the bottom of the kettle and you start to have bubbles rising. So the same type of thing here. And you have here a cut through a vertical. This is solved on the prismatic mesh. So again, this is kind of a randomly generated triangular mesh with equal background spacing here. And very close to the bottom, there is a cut which shows you the turbulence structure which develops in this case. And however, what was for us important was to confirm that we have a good quantitative results. So here you have just a selection, because we did very rigorous comparison on more key profiles, but you can see here a profile of the vertical velocity variance here on your left, and you can see the profile of potential temperature on the right, and the spectra as well in this cut. So this confirms that we have similar, and because this is our results are well confirmed by both experimental data in this case, and also are confirmed by our cross comparison with the structured meshes using OILAC, which obviously is a pleasing result for us. Okay, so I don't have really much time to go into spherical flows. We have repeated the same exercise on the sphere for the non-hydrostatic solution for the boundary layer, which you have seen a moment ago. But just really a mention that having all power from engineering on sophisticated mesh generators, which we brought to this work, it wasn't difficult for us to go towards solving, having meshes on the sphere and trying to solve the equations on the sphere. However, we have opted out for the geospherical framework. Well, why? Because in this case we are able to combine advantages and power of totally flexible meshes, which we can generate for unstructured meshes, with all the advantages which we all know with lat-long coordinates, which are, after all, a working horse of our many weather predictions and climate predictions models. So we opted for that, particularly as in our implementation, the issue of the poles, which usually is the issue with the lat-long coordinates, is easily alleviated by coarsening the mesh close to the poles, first of all. And secondly, we also have an elegant solution which is very straightforward and assures that we have a second order accuracy and full conservation with the pole treatment. So it wasn't difficult to implement. I appreciate that if you have some solutions which require special functions at the poles and so on, it may be more complicated. But in our case, it was a very straightforward solution which we could use. So just I will show you some of the things which you may remember or not from the Potsdam PD. We already had those solutions there. Those are hydrostatic solutions for a range of fluid numbers, and we have also which were compared were confirmed by the both experimental data and numerical data, and we also have done afterwards rigorous comparisons against both experimental and numerical solutions for the varying Rossby numbers. So really, to conclude, we could have some minor conclusions, but the main message which I would like to convey here is that there might be some implementation issues, but with the path which we have chosen, we do not see any substantial, huge, preventing us to follow with further difficulty, which is introduced by generalization to unstructured meshes.
I have a question, Joanna. For your unstructured mesh that you showed, I think 3 or 4 slides before, with the flow around a mountain.
Well, I think they were all mountains, so
I think
tell me when to stop.
No, that
This
one.
one?
Yeah.
Okay.
How did you refine the mesh? What was the criteria for it?
Well, this one, I did not use the adaptivity on this one. So it was just a design of the original mesh. Because
so you guessed basically where you...
Well, yes, it's an experience of the user. Okay.
Area.
Well, in fact, if you ever... Well, you are an expert on adaptivity, so I don't need to tell you that. In any adaptivity, let's say engineering, you still, if you want to have any joy with using adaptivity, your original mesh needs to rely on some of your experience. So if the mesh is completely inappropriate, you will not have enough information to refine it in the first place. So in this case, because the solution was known, there was, I could, for example, I could do the mesh adaptivity using the same solution. I just didn't have time as yet, perhaps here in 3D, because it's much easier to do it on fully tetrahedral meshes, mesh adaptivity. Here, if I wanted to do mesh adaptivity, I could do it on, let's say, one layer, but then I would need to carry it out through all the layers. So with the Delaunay triangulation type of adaptivity, what we do in engineering, and this could be readily introduced, is we use sources to adapt. So we basically define the regions where we can find the mesh, and then in order to prevent abrupt changes, we also have capability when we can specify how to relax the meshes away from the high gradients area.
In your nonlinear solutions, particularly those mountain wave simulations that are reaching and going through overturning, the solutions can be very sensitive to the essentially the subgrid turbulence or dissipation, whatever is being done to absorb that wave energy as the waves are overturning. And I'm just wondering how you dealt with that in comparing solutions on these very different grids, how the essentially the subgrid dissipation was handled.
It was so-called ILES. So numerical methods are monotone and they prevent development of any spurious oscillations. So there is no explicit subgrid scale model. Everything is delegated to the numerical method.
Yeah, I can appreciate that, but what I don't see is why that necessarily gives you the same answer in both cases, because the way that
Oh, you mean
The
that
way
we
that-
only show the picture, not show any measure of the... That's what
Is that the point you wanted to come in?
Yes, I want to something that Piotr should be saying. What I find very attractive about the MP data approach is that it uses basically on an analytical level a dissipation mechanism in the numerics, which means there is an upwind discretization, which is sort of straightforward, and you can do it on any mesh. And then you do the same technique again, an upwinding, for the error equation, essentially. So that what you do in doing the dissipation in MP data doesn't really depend on the mesh at all. It's on a sort of a more abstract level that you can do on any mesh. In that sense, at that stage, I'm not surprised to see very similar results with MP data on those grids. If you try to do this with finite volume, classical finite volume, where you have to do reconstructions on the irregular meshes, there it's very tricky to get the same results. I would immediately agree with you. But with MP data, I can see why that happens.
But how does that make it physical? I mean, it's all because of the numerics.
It doesn't. It's
So-
a dissipation
I
mechanism.
mean,
But you have that problem with any kind of scheme, and of course you can supply MP data schemes also with subgrid models for the turbulence. I'm just trying to explain why I do understand that the two grids give essentially the same results for that case when nothing is done.
so you're saying that even with a very fine mesh, you're going to get the same amount of dissipation as if you used a very coarse mesh.
No, that is not what I'm saying, but
So-
on comparably
Our solution
refined
is going to be the
grids.
same.
But this is the coarseness or refinement of the mesh. The meshes are they have about the same resolution. The details are in shade.
Yeah.
We are not comparing coarse mesh to fine mesh here.
We are
For
from
this
a different
big wave.
shape of the mesh.
Well, it looked to me in some of these unstructured meshes, you were grouping a lot higher.
No,
mesh
those were like this was the resolution that like a structured grid code would have. It was coarsened toward the boundary.
So where we didn't have anything worth resolving, then we use much coarser mesh than it was required, which saved us a lot of redundant number crunching in the points.
Let's put it differently. Where the action was, the resolution was about the same for everybody.
Frank.
So in your conclusion, you said that there's no difficulties with these models for unstructured meshes.
Well, there always, arguably, you will always be able to find difficulties. Obvious one is that if you want to use parallel computing, okay? Obviously, parallel computations on unstructured meshes is substantially more challenging problem.
Yeah, but it's not a deal breaker.
But in terms of the numerics, there isn't anything which we can see at the moment from our work.
And that was my question. What was it that you were thinking you would see? It sounds like you were thinking of a question and that answered your question. What was the question you were
Well,
asking?
we were always hopeful, but everybody was telling us that it would not be possible. So, well, here we are.
What was the reason? Why
I
would you?
can answer this. From what I saw, the opinion in the engineering community expressing a number of papers is that actually unstructured meshes are less accurate than.
Oh well, but that's not a valid point, because this is purely historical. Because most of the codes which give this impression is because they have been derived straightforwardly from the structured codes which use the orthogonality conditions for accuracy.
Oh,
Okay?
this is one.
So if you have a purposely, properly derived code for arbitrary meshes,
So you're trying to answer the question for, in generally for unstructured meshes, not just unstructured meshes with an elastic.
well, not necessarily. I think there was people haven't done it before, okay? So there was always a question. Is there anything which would prevent solvers to work when you don't have a nicely orthogonal meshes which have special properties?
Like, think about elliptic.
When you have, you may recall some of the papers alerting community quite correctly that if you have abrupt refinement of the mesh, for example, by nesting, you may have reflections from the boundaries, okay? So again, question, how do you have a good quality of the mesh, which has much higher demands for atmospheric flows than for engineering flows, so in terms of how gentle is the smoothness of the mesh between the coarser and finer. So this type of issues we need still to explore, and well, at the moment we don't see any difficulties providing you use common sense and don't produce criminal meshes. Okay. So we don't seem to have a problem of this sort. Perhaps one more comment which kind of relates to your earlier question about the speed. With the same numerics, I have developed together with Piotr the transonic from high-speed compressible flows, NFT data solvers, Runge-Kata based, and I compared identical implementation of numerics with the Runge-Kata solution, and they were identical. Okay, so there wasn't really very with NFT, FCT being usually judged to be an expensive part. This was similar to the expense which was.
But I think the real question is whether the soundproof equations with the Poisson equation, what is the comparison of cost between having full Euler equations with solved semi-implicitly with a Helmholtz equation? That's the
well, I know that it was, but on the other hand, I heard informally people saying that MP data is so incredibly more expensive. So after hearing this, I did the check. So for the compressible high-speed flows, it is not. It's the same as Runge-Kata. We also have implemented it in AWE, arbitrary Lagrangian numerics for hydrocodes, and we found that it's cheaper than muscle sims.
Yeah, at that point we'll go two more questions and then we'll get a coffee.
The mesh you showed looked very isotropic in the vesicle. What is the maximum aspect ratio of your elements when you do large scale deep atmosphere simulation?